Okay, here we go again. Another lesson in Chapter 8. Still we're dealing with quadratics. This time we'll be talking about formulas and some of the ways we can use them to solve problems, how we can use them to, we can rearrange them kind of to solve for a different variable than the one we originally had. I thought I'd get a little bit more interesting color here. Okay. So, second degree formulas. Just another way of saying quadratic. And then we'll solve some problems using quadratics. Remember, we start out with a few minutes devoted to the previous lesson, getting us set up to move forward. A to the sixth, well, when did we ever learn to solve this? We actually didn't. However, if we could convert this into a quadratic, then we'd have something we're familiar with. We could solve it. What was the rule we had there? If we have this set up in standard polynomial form, that is, descending power order, highest power first, then the next, so forth, then we can look at the leading, which is sixth power, and the middle, which is third power. And what's the rule? If the leading, the power on the leading is twice as much as the middle, then we can convert this into quadratic. And to know what we're going to use for our conversion factor, we look to the middle term. We're going to say let u be equivalent to x to the third power, which means that u to the second power is going to be x to the sixth. So let's rewrite that. X to the sixth is going to be u squared minus 7u plus 10 equals 0. Now every time you are looking at a quadratic, you start thinking of the zero product property. In this case, we've already got the zero. That's good. But we've got a sum of terms, and we want a product of factors. Can we convert this into factors? I think so. U squared. So this first one has to be u times u. And then a positive 10. So we're looking at for two factors of 10 that when we add them together will give us a negative 7. What would those be? Well, obviously they're both going to have to be negative because they turn out when they multiply together to be positive. So they're both the same sign. And that middle sign is negative. How do those look to you? So we've got a u, which is equal to 5, right? We had u minus 5 equals 0. And we work with that a bit. We get u equals 5. U minus 2 equals 0. We work with that a little bit, and we get u equals a positive 2. We said in the beginning that u was equal to x to the third. So that would mean what? How are we going to figure out what x is? That's right, we're going to take the cube root of both sides. So we get x is equal to the cube root of 5. And we can go through that whole exercise again right here. We substitute in what u is equal to, x to the third. Then we solve for x, and we get x is equal to the cube root of 2. So there are our answers to that one. This next one isn't quite so obvious, I don't think. But let's convert it over to rational exponents. You're going to find that rational exponents can often be deciphered a lot easier than radicals. So we've got x to the first power minus 4 times x to the what power? Power of 1, root of 2. So we could say the power of 1/2 plus 4 equals 0. Now we're interested in knowing whether or not this is reducible to quadratic. If it is, then the leading term, its exponent, should be double what the middle term is. Well, it's not obvious, but this is 1, and I could write 1 as 2 over 2, couldn't I? That's just a fancy 1. And clearly, 2/2 is twice 1/2. So yes, this is reducible, and I can say that u is equal to, remember we take the middle, x to the 1/2. And u squared is equal to x to the 2/2, or plain old x. So x to the 2/2 is u minus, u squared. Oh, how could I forget that already? X is equal to u squared minus 4u, because u to the 1/2 is u. Excuse me. X to the 1/2 is u plus 4 equals 0. Zero product property now. We have our 0. We need a product. Again, it's going to be u times u in order to get u squared for the beginning. And then over here, we've got a 4. What are two factors of 4 that when we add them together will give us negative 4? Very good. Now you can see that we've got redundant factors here, which means we will have redundant solutions. I'm just going to work with one of them. U minus 2 equals 0. When we solve for u, will be u is equal to 2. We know u is x to the 1/2 or the square root of x. You could write it either way, whichever you prefer. But I'm not interested in what the square root of x is. I want to know what x is equal to. So I'm going to undo the square root by doing the opposite operation, which is squaring. So I get x equals 4. How neat is that? There we are. Just a little review to set us up for the next lesson. All right, let's see if I can figure out what we're after here. We've got a formula here. We want to solve for a. Now, I recommend to you, whenever you're doing these, keep your eye on the prize here. You know you're looking for a. Keep that in view all the time. Right now, a is inside these parentheses, which are raised to the power of 1/2. So that's the same as, yes, a square root. Anytime we've got something trapped in an operation, we can release it. Well, at least when it's in an equation. We can release it by performing the opposite operation. What would be opposite to taking the square root? That's right, we can square both sides. So let's do that. We'll square this side, and we'll square this side, and we will have m squared is equal to, what happens when I have a power of 2 over a root of 2? I end up with 2 over 2, which is equal to 1. So we can simply say AB. Remember, I'm looking for A. It's not by itself yet. It's being multiplied by B. Same rule applies. We want to undo the multiplication, and we do the opposite operation, which is division. I'm going to divide both sides by B. Of course, B over B will be 1, and I will have A is equal to m squared divided by B. So if I was doing some sort of scientific inquiry or something where I needed to solve for A and I knew what M was and I knew what B was, it really would be worth my while to take a minute before I got started and solve for A. How about this one? Solve for D. This one is even more complicated because D is certainly trapped here in a power relationship, right? Not maybe what we usually think about, but it's being squared. There's another problem, though, isn't there? It's not only in this power relationship that we want to get it out of. It's also in the denominator. We're going to solve for D. We want it in the numerator. What could we do? Well, we certainly could multiply both sides of this. Let me write it down. F equals M over D squared. And remember, we're looking for D. Keep your eye on that all the time. I do not like D squared being in the denominator. We have a division by D squared, so what's the best thing to do? We'll undo by the opposite operation, which be to multiply both sides by D squared. When I do that, I've got D squared in the numerator and the denominator. They cancel each other out. I end up with F D squared equals M. Now I still have D in this power relationship here that I don't like, but before I can tackle that, I need to get rid of this F. Remember, we're always trying to get D all by itself. So let's divide everything by F. Right now it's being multiplied by F. I'm going to do the opposite operation, which is division. So I've got D squared equals MF. M divided by F. Now, what would I do to undo this? I would take the square root of both sides, plus or, let's see. Okay. Oh, I just wiped it out. Sorry about that. So I've got D squared is equal to M divided by F. I'm going to take the square root of both sides. And of course, it's going to be plus or minus on this side. So I end up with D equals plus or minus the square root of M divided by F. There we have it. Now let's just talk about some of the general rules that work every time. In most formulas, the variables represent something you can measure, and usually non-negative. So some of the problems we ordinarily come into with regard to you can't let a numerator go to 0, oftentimes that becomes a moot point. We don't have to worry about taking absolute value signs when taking principal square roots because of that. This is such an important point Please pay attention to this one. Operations which are opposite undo each other. Okay, let's just focus on that, because this is universally true. Operations which are opposite undo each other. And we can use all kinds of examples. We can use, if you're multiplying, then if you divide, you undo it. If you're adding, then you can subtract to undo it. If the same operation is applied to both sides of a true equation, the result is a true equation. This is another really important point, isn't it? Because this is what equations give us. If you're working with an expression, you don't have the same freedom that you have with an equation. When you see this equal sign, it gives you a kind of freedom, because you can do anything you want to this side. Anything. And as long as you do the same thing to this side, your equation will remain true. That's a very powerful concept. Finally, we're going to do a word problem here. When an object is thrown, okay, so we've got something we're going to throw into the air. The height in feet is given by the formula h minus 16 times the time squared, and the time here is going to be in seconds. HO is the initial height. So what I just did, this would be HO, that's the initial height, and the height that it achieves, assuming that this is our 0 point, the height that we're solving for is right here at the apex, at the maximum. So let's try it with an example here. If a stone is thrown upward from a height of 8 1/4 feet, so our initial height is 8 1/4, with an initial velocity, that's v sub o, of 64 feet per second. And notice our units are what they're supposed to be, feet, and when we're talking about time, seconds. How long does it take for the stone to fall to ground level? Well, that's this t, isn't it? We want to solve for t. T. What is t? Now, there's two ways we can do this. We can just plug in these values right now and then solve for t. Or we could take this formula here and solve for t to start with. I think in this case, where we only got one problem to solve, let's just put in these values. So it's thrown upward from a height of 8.25 feet with an initial velocity of 64 feet per second. How long does it take for the stone to fall to the ground? Oh, well, if the height we're interested in is right here, we can say that we're talking about the time when this height becomes 0. So we've got 0 for our h equals negative 16 t squared plus, what's our initial velocity? 64. 64. And that's times t, plus our initial height, which we said was 8.25. How else could I write that? I could write that as What's 4 times 8? 32. I could write that as 33 over 4. Is that 8.25? Is it? So 0 equals, if I multiplied this whole thing by 4, just to get rid of this fraction here, what would I come up with? Well, 0 times 4 would still be 0. Instead of having minus 16, I'd have minus 64 t squared. 64 times 4 would be what? Well, 4 times 4 is 16. 256 plus, oh, I hope I'm right, 256t plus, if I say 4 times 8.25, I get 33. Oh, that is one awful thing to look at. And here's where I should have my calculator handy. I hope you have yours handy. Let's extend this page. I'm going to do that factoring by grouping. We've got minus 64 times 33. I don't see any possible way to simplify this. So I'm multiplying these times each other. You're probably doing it a whole lot faster than I am. This is going to be some negative number, right? 2, 1, 1, 2. So I'm looking, these are awful. I'm looking for two factors of negative 2,112 that when I add them together will be equal to a positive 256. Really? Two factors that when I add them together will be equal to a positive 256. Well, yikes. So what's half of this? Maybe that's one way to look at it. That would be 1,056 times negative 2. I add those together, I sure don't get 256. Well, let's try dividing this in half again. That would be 528, right, times a negative 4. And that doesn't get it to me either, but maybe with this next one I will get there. What is half of 528? Well, it'll be 250 plus 14. So 250 plus 14, 264 times a negative 8. You know, by God, that does it. That does it, doesn't it? So we can, because if we add a negative 8 to a 264, we get 256. So I didn't think I was going to be able to do this without my calculator. So we've got a binomial squared here of, oh no, I'm not going to handle it that way. Just a moment. I'm going to do factoring by grouping. And I hate having a negative here. So why don't I multiply everything through by negative 1, and that'll give me still a 0 here, 64t squared negative 256t negative 33. The only thing that's going to do to what I'm going to use is I'm going to use a negative 264 and a positive 8. So now factoring by grouping, this is still a 0, and I'm not going to touch my first term. That's going to stay exactly the same. I'm not going to touch my last term. That will stay exactly the same. But remember what we do here? We divide this up. So I'll have negative 264t plus 8t. Those are equivalent to what I had before. I haven't changed any values here. I've just re-expressed them. So, do you mind if I put my 0 over here? And this would be 64t squared, and this, I'm factoring by grouping, remember, and then I'm going to group these two. So if what can I factor out of here? 8t, can't I? Let's try it. 8t leaves me with, I might be able to do something better than this. We'll see in a minute. Leaves me with 8t minus, and if I divide 264 by 8, 264 divided by 8. I think that will go in nicely. Let's see, we get 324. Oh, I love it! You see what's happening, don't you? So we get that nice 33. Plus, what can I factor out of these two? Just a 1. So I've got 8t minus 33. Oh, this is where algebra, it all comes together for us. This is great. So I have a common binomial here, which I can factor out. Let's do that. 8t minus 33 times, what's left behind after I factor that out of there? That's right, 8t plus 1. So we're going to solve each of these in mini equations, and we get 8t minus 33 equals 0. I'm going to skip that step and say, okay, it's equal to 33. So t has to be equal to 33 divided by 8 seconds. Or in the case of this one, I've got 8t plus 1 equals 0. Or my next step, I subtract 1 from both sides. And I'd have t is equal to a negative 1/8 second. Well, what do you think of that, negative 1/8 second? No, that's not. We're not going backwards in time. So there's our answer. Hallelujah! What a nice problem. We'll see you back in class.